Welcome back, folks. Today in Chapter 10, we're continuing our look at area. In 10.2, we're going to look at areas of trapezoids, rhombuses, and kites. Oh my. Objective to find the area of trapezoids, rhombuses, and kites. Pretty straightforward. Here we go with that. So let's start off with the formula for the area of a trapezoid. I'm going to say the area of a trapezoid is half the product of the height and the sum of its bases. So 1/2 times height times, in parentheses, b1 plus b2. Now with the trapezoid, we're going to say that the two parallel sides are the bases. So b1's on top, b2's on the bottom. And then just like with the parallelogram, I'm going to say the height is the distance between the bases, okay, at a right angle to the bases. Okay, so we have our b1, our b2, and our height. Again, area is equal to half times height times b1 plus b2. All right, where the heck is that formula coming from? Well, let's take a look. Let's take a trapezoid. I'm going to make a copy of it and flip it around, connect it like so. So I have a parallelogram now, where if we have the top of the original trapezoid was b1, we'd also have a b1 down below. And bottom of the original trapezoid was b2. We've got a b2 up top now. Okay, so we have a parallelogram. I know area formula for a parallelogram is area is equal to base times height. So we have our base. Oops, that red doesn't show up on red, but oh well. And then we have our height running between the bases. Okay, now what is this made up of? Area is equal to the height, and the base is really just this b1 plus b2. And where the half comes into play is I don't want two trapezoids, I only want one of them. So we'll get rid of one here. Okay, that's where that half's coming from. Okay, so really, same formulas for our parallelogram. Okay, just a little bit different when we split that trapezoid, the parallelogram, in half into two trapezoids. Let's look at using that formula then. Okay, we said area of a trapezoid is equal to 1/2 times the height times b1 plus b2. Now with this problem, we have some of the information we need. We're going to have to solve for the others. So let's fill in what we have right away. We could say area is equal to, we have the 1/2, that's always going to be there. Okay, I don't actually know my height for this problem. Okay, but I do know the base 1 and base 2. We could say base 1's 8 and base 2's 14. And then the trick for this problem is going to be solving for that missing height, okay, figuring out what the distance between the bases are. And to do that, what I can do is I can use this angle here, this 45 degrees. I can break this trapezoid into a right triangle. And I know that the bottom side of this right triangle is going to be 14 minus this 8. So as in 6. And I want to solve for this h, okay, the side opposite to the 45. Okay, so I want the opposite side of the triangle. I know the adjacent. Okay, I can always use an angle and one side of a right triangle to solve for the other side using trigonometry. Okay, opposite adjacent, that's my tangent ratio. We know that the tangent of an angle A is equal to the opposite side over the adjacent side. Okay, filling that in, we could say that tangent of 45 degrees is equal to opposite, which is the h, over the adjacent 6. And then to solve that equation, I'm going to multiply both sides of it by 6 to cancel out my fraction. So we end up with h is equal to 6 times tan 45. Plug that into the calculator, and we end up with a 6 once again. All right? So using some trigonometry to solve for a missing part, and really that's going to be the hard part of this problem. From there I can plug the 6 into my equation, and then I can just multiply things through using the calculator. So a half times 6 times 8 plus 14, and we end up with 66 for a total. So we can say 66 millimeters squared. All right, that's an example of using our trapezoid area formula along with using some trigonometry to solve for a part of the figure. Okay, part B is the same idea. Why don't you take a minute, pause the video, try to work through part B, and then, or if you get stuck or to check your answer, hit play and check out how things go. All right, let's run through part B quick. So we've got our formula. Now this one we don't know the height of the trapezoid once again, but I actually also don't even know the other base. Okay, so we know base 1 on top is 7, but we're not sure what this bottom base is. Now it's going to be made up of a 7 and another chunk here, which we'll call x. So for this problem, there's two parts to solve for. We've got to solve for the height, then we also have to solve for the missing piece of that other base. Okay, to do that, we'll use the hypotenuse that we're given for this triangle we can break things down into, and the 60 degrees here. Okay, again, we know the hypotenuse, and the height, the h, that's the opposite side. Okay, so I can use my sine ratio. Sine of a is equal to opposite over hypotenuse. Filling that in, we can say that sine of 60 is equal to opposite h over hypotenuse 4. Multiply both sides by 4. We end up with h equals 4 sine 60. Which turns into a 3.5, we could say. Okay, other thing we need to solve for is this adjacent side of this right triangle. Okay, so we have hypotenuse and the adjacent, that's the cosine ratio. I can say that cosine of A is equal to adjacent over hypotenuse. So cosine 60 is equal to the adjacent x over the hypotenuse 4. Again, multiply both sides of this equation by 4. And we end up with x equals 4 cosine 60. In other words, x is just equal to a 2. All right, we've got all our missing pieces solved for now. We can say area is equal to 1/2 times the height which we just found, which was the 3.5. All right, times base 1, which is the 7 we were given. Okay, plus base 2, which is a 7 plus 2 for this entire distance down here. So 9. All right, plug all that in, and we end up with a 28. We could say meters squared. Now we're also going to look at the area formulas for rhombuses and kites in this lesson. Now nice thing is both rhombuses and kites have the exact same area formula. I'm going to say the area of a rhombus or a kite is half the product of the length of its diagonals. So area equals 1/2 times d1 times d2. Okay, so for rhombuses and kites, we have half times d1 times d2, where the diagonals, once again, are the distance from one corner to the opposite corner, okay, of our rhombus or of our kite. Now, as far as where that formula is coming from, if I have a rhombus with the diagonals, basically what I can do is I can pull it apart and turn it into two triangles. Okay, now we know the area of a triangle is equal to just 1/2 times base times height. Okay, where my base in this case we could say is D1. Okay, that was a diagonal of our rhombus. And the height is just half of D2. Okay, so we'll replace the base with the D1, the height with the D2s put together. Okay, we have the half. That's where that half times D1 times D2 is coming from. Okay, it's just area of a triangle. All right, let's go ahead and use those formulas. Problem 2, part A, looks like we have a kite. Okay, we know its area formula is 1/2 times D1 times D2. So we have area is equal to 1/2 times diagonal 1, we could say is the diagonal runs from upper left to lower right. Okay, it's made up of two chunks, a 3 and a 3. So we could say 3 plus 3 is 6 for that D1. Okay, times D2, which is the other diagonal, it's made up of a 5 plus 3, so 8. All right, half times 6 times 8, that's going to give us a 24. So we can say 24 centimeters squared. Now in part B, notice we don't have all the information we need to use this formula. Okay, so we have for a rhombus in this case, just like with a kite, area is equal to 1/2 times D1 times D2. Okay, now we have one of the diagonals, the 10. What we need to do for this problem is just like the trapezoid, we need to solve for this other diagonal. Okay, to do that, I'm going to break this problem down into a right triangle. Okay, one fun fact we had from way back in chapter 6 is diagonals of both kites and rhombuses are perpendicular to each other. Okay, so I have a right triangle where if I split this diagonal in half, I get a 5 on both sides of it. Okay, this missing part here, we can call that the x. And if I have two sides of a right triangle, I can solve for the third side using Pythagorean Theorem. A squared plus b squared equals c squared. Okay, where my hypotenuse, my c, is my 8. Okay, the x and the 5 will be the a and b, so we can say x squared plus 5 squared. All right, so we can say that x squared plus 25 is equal to 64, squaring things out. And if I subtract 25 from both sides, I end up with an x squared equals 39. And when I take the square root of that, I get x is about 6.2 units, we could say. Okay, so that's going to be the hard part of the problem. We solve for this x, this 6.2. Now the trick here is that this diagonal is made up of two chunks that are both going to have lengths of 6.2. So this entire diagonal will be 6.2 plus 6.2. So in other words, 12.4. And then once I have that missing diagonal, I can multiply the half times the 10 times the 12.4, the diagonal we just solved for, and end up with a 62 inches squared. All right, so just like with our trapezoid problems, we might need to solve for missing pieces, and the way to do that, the way we saw in this lesson, is to break things down into right triangles and use either sine, cosine, tangent or Pythagorean theorem to find those missing parts.